So this is the first episode, physics in the PM, or if you're in Australia, physics in the AM, episode one. Do you? We'll just see if how many people kind of trickle in here, and if not, then it'll be a good conversation just between us. Can you hear me?
Yeah, I can hear you, mate. How you going?
I was going great, going great.
Awesome. Yeah, good to hear your voice. I've been chatting to you a bit. That's the first time I've actually heard you talk.
Yeah, I've been trying to avoid talking on these things, and then I don't know. I get you get on these crypto Twitter spaces, and people start talking about physics, and I'm like, I you know, I like talking about physics. I don't
Yeah,
really
man.
care to
Yeah.
talking to people that I don't necessarily know if I can't see their face. But then I'm trying to get over that, you know.
Yeah. Yeah. Look, I think it's one of those things where we're sort of looking at crypto charts all the time, and we're sort of talking about this sort of stuff. But sometimes it's good to take a bigger picture sort of look at sort of the world around us, and touch some grass, so to speak, and talk about other topics. Um, and when you were talking about um, having a space sort of dedicated just to physics, I thought, oh yeah, I'll be in for that for sure. And quantum entanglement is just one of those subjects that's always been, really fascinating for me. So I'm sure there's plenty of people out there that would find it interesting and maybe get something out of it.
Right, and I think a lot of people like to use analogies in physics, especially in crypto. Uh, I hear them all the time, and then I hear them talking about the dynamics of the price modeling. They want to talk about like diffusion. It's essentially it's like a diffusion model to describe prices, and thermodynamics comes into play there. And then he loves to use physics analogies, and so it's kind of like the big picture. And what he used the double slit experiment, the observation, and I think at that point I was like,
Okay.
it's time. Plus,
Yeah.
I was talking to Chef Omakase about gravitational waves. He was very interested in gravitational waves, so I went on his
Oh
space, and
wow.
when we were
Oh
talking
wow. Okay,
about
I didn't
that,
realize.
yeah, and
Yeah, because
so
I worked in a gravitational wave observatory for a brief period.
oh, cool, cool.
Yeah, yeah. So that's definitely something we can chat about as well. Um, but yeah, you're right about that being a lot of analogies in physics with economics and stuff like that. A lot of people talk about economic energy, um, and entropy and things like that. And a lot of people use Fibonacci tools, and there is some sort of crossover between sort of the natural world and finance, I think, definitely. And when you're talking about liquidity in an asset, and you're talking about how hard it is to move the price, you kind of get ideas of momentum and scale of weight and things like that. So something might be quite heavy if it's got like a large liquidity. It's hard to move that asset. So these are all physical, things that help us understand, markets.
Right. I mean, like arbitrage theory is essentially like a gauge theory, where you go from one currency to the other. And so that bonded liquidity, like you're talking about, there's just a natural physics language that arises from there. Hex Funks, thank you for showing up. Appreciate you. We're just kind of talking right now and just kind of waiting to see people come in. Um, so
Yeah, man.
I
So
think
I was just going to say one thing that might be good for people is like, well, first of all, I guess you're a physicist. You've got a PhD. What's your specialty? What's your field of sort of specialty?
so. When I was in grad school, I worked in quantum gravity, so quantum field theory, quantum gravity. I was interested in some certain models of that. And then after I left grad school, I work in somewhat lower energies now. I can't really go into a lot of detail about what I work in now, but I'm a lead scientist on a project. Um, but I also continue researching on the side. So I keep my fingers in the pulse of what's going on in high energy theory. I'm really interested in, and so on my side projects, I'm really interested in like quark confinement, and so I'm also starting to reconsider some quantum gravity models and the difficulty of quantum gravity, which I actually kind of want to talk about a little bit tonight about if we get an opportunity talking about the Heisenberg cut. But I think maybe what we do at the first, so what? Let's go into what your background is.
Okay, sure, sure. So, yeah, I've got a degree in physics and pure mathematics. I basically specialized in astrophysics and particle physics. I worked in a gravitational wave observatory for a while. And basically now I work in an electromagnetic compliance laboratory. I've been working there for about 20 years. So I've got a lot of, experience with electronics and specifically to do with electromagnetics. But, my passion has always been quantum mechanics and astrophysics and particle physics. And yeah.
I think once you get that bug in you, it never really leaves you. Like I always, whenever I come at a problem, regardless what it is, I'm a first principle type of thinker. So I'm like, okay, so what's the underlying dynamics and trying to understand, what the actual physical processes that are occurring when I'm doing any of the analysis. So pure mathematics. So your degree. So I think X-Funks is in the U.S. I'm in the U.S. The education system's a little bit different in Australia. So
Correct.
right. So we go through like undergrad where we're taking general education and all this stuff along with a major, and
Yeah,
then
so I had an undergraduate degree just, in science, where I did computer science and all that sort of stuff and physics and engineering and mathematics. And then I did a double major in physics and pure mathematics. So I guess still at an undergraduate level, but they were my majors, but it's not a PhD. So um,
no. But I mean, did you have like general education where you're taking art and history and those kind of subjects?
not really, no. Everything I did was exact sciences, like
Yeah,
group theory, mathematics, cryptography, chemistry, particle physics, astrophysics, all that stuff. That's quantum mechanics. I actually did,
that's
study quantum mechanics at tertiary level. So
that's awesome. I mean, so that's one of the things that you're kind of gearing in that you're not bogged down by a liberal arts education.
no, no.
There's right. I think that's a big shock. Like I was telling you before, one of my friends from grad school, she went to Queensland, and she was basically telling me the same thing, and I was like, wow. I mean, it's just so much more efficient of a system, and then the
Yeah, I
cost.
didn't realize that that's not how it's done over the US. Yeah.
Yeah, no, we you don't really specialize. I mean, you pick a major, and you start taking your major courses like your freshman year, but then but you also are required, but based on the accreditation of the university or the college that you go to to take, you know, psychology and
Yeah.
art
Yeah,
history and all this stuff. So
I did actually sit in on a few psychology lectures, but that was purely because as I was walking out of my physics lectures, I noticed the psychology lectures had all the hot chicks in it. And I was like, the hell's going on here? Like, it's a sausage fest over here in physics. And then as I'm walking out, there's all these hot chicks doing psychology. I'm like, I think I need to stay in this theater. That's what I need to do. So I actually took a few psychology lectures, but for different reasons.
That's hilarious. Okay, so I don't know how many people we're actually going to get in here, but that's okay. It's just a start, and Hex Funk's took a break today, and he absolutely deserves it. So he knows how it is getting started. So let's since this is getting recorded, and when somebody may listen to it later on. So let's put some context in this. What is quantum
Sure.
mechanics?
Yeah. Okay. Well, so an easy way for me to describe it to people has always just been quantum mechanics is the study of the subatomic. So most people are familiar with atoms and things like that, however you want to think of them as being represented. But anything at smaller scales for particles, electrons and scales below the atomic, that's probably the best way to think of quantum mechanics. And then there's also this probabilistic nature. When you're talking about quantum mechanics, you're intrinsically sort of talking about how particles they don't have concrete parameters, but rather they have probabilities of having parameters. And particles can exist in probability states. So I think that's a fundamental way to describe quantum mechanics.
Yeah, I think that's a really good explanation. I think you know general framework of discussing dynamics. Physics is about like the dynamics, the interactions between matter and energy, right? And how things move and how things evolve in time. Um, and so, yeah, I think that's a great, uh, explanation. And
Yeah,
so,
yeah. And one of the things I was going to say is we, sh- we we should probably talk about some of the history of how how quantum entanglement sort of came about, because it has evolved as a theory from its inception and into its experimental sort of stage. But maybe you could talk a bit about the early EPR paradox, Einstein sort of asserting that God does not play dice with the universe, and his sort of almost rejection of that probabilistic interpretation of reality.
yeah, so there were, even though Einstein, it's kind of interesting, Einstein with quantum mechanics, because he's kind of one of the fathers of quantum mechanics, and I don't think people give uh, quite understand that relationship, because 1905, one of his fundamental papers is over the photoelectric effect, which is a quantum mechanical process. And so he kind of took some of Planck's ideas and fleshed them out even more, and to give rise to the the quantization of the quanta of light, as it were. But I think you know relativity plays such an important role in this discussion, because uh, things are inherently, there is no now, right? I mean, the concept of now and the concept of locality is so intimately tied with special relativity that he starts to have this worry, because it looks like things are inherently non-local, and which would
Yeah.
seemingly break um, uh, break
Classical
special
physics, I guess.
relativity. You have
Oh,
yeah.
yeah,
So
yeah.
locality is yeah. It's all about, do you have a signal that's faster than the speed of light, right? So
Yes. Yeah.
right.
So
So
I
the
think
way,
one way you could kind of describe this. Now, this is possibly just because we've come from a crypto sort of background where people understand, blockchains and things like that. But
right.
you could almost think of it as if you have this scientific consensus and it's proved through experiment. You can have theories, but at the end of the day, it has to align with experiment. It has to be repeatable. It has to be repeatable at laboratories around the planet. So at some level, there was a point where there was almost like a fork in the scientific consensus where Einstein started talking about relativity, like you're talking about, where special relativity, talking about speeds approaching the speed of, items approaching the speed of light, having length contractions and having time dilation. So it was this idea of non-linearity of time, and that with general relativity, this notion of curved space-time, where the mass of something could deform not only the space and the orbits and things like that, but also deform time itself. So you could get time dilation, and which has now been measured with atomic clocks. You know, you can measure
it is one of the most tested theories in the history of physics. Is general relativity. I mean, geosynchronous orbits, but really, but both of those problems, both special and general relativity, really was in the framework of local physics. Physics acts locally. Things are not, happening on Earth that's affecting things that are happening on Mars or whatever. And so that the notion of locality is very important. And then Heisenberg, so quantum mechanics, you were talking about probabilistic nature. Quantum mechanics is really, in my mind, it's really all boils down to the wave function. And what is the wave function? Wave function describes the state in which you are determining the dynamics of a system, right? And so it's about the evolution of this system, and what can we observe about the system. So we got a set of observables, we have a set of states, we have a set of observables, and then, as you were saying before, we have these superpositions. So Einstein, around 1935, and I think you had a really good idea. Maybe in the future space we'll do this. Well, we're a little bit more. I'm a little bit more prepared. But in 1935, him, Podolsky, and Rosen wrote a paper in which they were refuting some of the claims of quantum mechanics, in which they said, okay, well, there has to be something more physical than the wave function. They imagined a decayed particle, and the two decay products were going in opposite directions. And then they would say, well, if we measure the one momentum from particle A, it's going along the x-axis at negative h bar k in some units. We automatically know within a relative small uncertainty that the other one is traveling at h bar k. So the opposite. And we can also tell the distance between the two with an arbitrary preciseness. Which is a violation of that probabilistic viewpoint that you were talking about, which goes into the non-commutative. The position and momentum operators are not commutative. So you can't know simultaneously with infinite precision the position and the momentum simultaneously.
Yes. And so that idea of like Heisenberg's uncertainty principle, where you require the observer so you couldn't know the position and the momentum at the same time, because the process of measuring the position of the particle affects its momentum. And likewise, you can't know the energy and the frequency of a particle, because it's the act of measuring that actually changes either property.
Right.
So
And
that
that's
idea, is really interesting in terms of like we're now inserting the role of the observer into experimental measurement.
cor- correct. And that's really where the breakdown starts from is the measurement problem. Like how do you know something? Well, you have to know it by measuring. And I think when I first came across this, these kind of thoughts, um, back a long, long time ago in a galaxy far, far away, I started thinking about it in terms of people wanted to talk about consciousness. Does consciousness imply measurement? Do you have to be conscious to apply a measurement? And that seemed not correct.
Yeah,
Uh,
there is an element of philosophy that sort of branches from this, and there's a lot of ideas where people kind of talk about, that if a tree falls in the woods and there's no one around to hear it, then it doesn't make a sound. Of course it makes a sound. It's just there's no one to hear it. So, but then is reality defined by someone observing it, or really just the phonon, the sound that comes from a tree breaking the vibrations, that exists whether you're here to observe it or not. But that's
or
very different from an actual, well, from Heisenberg's uncertainty principle, where the observer, or if with quantum entanglement, where the observer actually plays a role. So by having
correct,
an
by having
entangled, yeah,
interaction with that entangled state. Yeah, absolutely. I mean,
yeah.
so
So go
the
ahead.
what I was saying about the reason that they're saying that this was incompatible is that basically they can show that there were that they could eliminate some of the uncertainty, and that arose a paradox of, hey, Heisenberg is saying this picture of quantum mechanics is correct. We're giving you an example where something looks strange because we can tell you where these things are, and then we're going to do a little math trick and say, okay, well, because I have momentum and let's say my system is translationally invariant, which basically means that I can move the system arbitrarily far apart, that I could still tell you what's happening on particle A. I can tell you what's on particle B by performing a measurement on particle A. And that's where the real disconnect, because if you take that to the extent, and this is why I'm saying this is a kind of a mathematical trick, but that translation of that system where you can get them space-like separation, then you have what looks like an acausal signal, so something faster than the speed of light. So you have something inherently non-local occurring
Yeah, I
through
think
the
that's exactly
collapse of
why.
the.
So, sorry, I was just going to say, I think that's exactly why Einstein had such a big problem with it.
100%. I mean, it's like it's 100% what reason that his the problem with it was because the measurement the, the measurement essentially instantaneously collapsed the wave function. Uh, Now that there's some dispute on that that terminology now. There's lots of schools of thoughts about the measurement. How does the wave function actually collapse? There's a whole branch of foundational quantum mechanics people, and it's really fascinating to hear them talk. But
Yeah,
anyway,
yeah. So I think one thing I should clarify just for the audience as well is that there are some things that we're discussing, like the history of how the EPR paradox came about, how Schrodinger and Einstein sort of refuted the sort of models that the probabilistic models that Bohr had come up with, the Copenhagen interpretation, and then, but indirectly they ended up sort of proving the quantum mechanics is actually real, and so some of these things, they're not up for debate, if you know what I mean. Like in terms of like these things happen, like the history happened, and then
no,
so
absolutely.
the experiments happen at a later state, and we use quantum entanglement in quantum computers, cryptography, all sorts of uses. So a lot of these things are sort of not up for debate because they are experimentally proven. What is, however, possibly up for debate is the how or the why. So, like you say, with the mathematical tricks, physicists are very good at using maths to make things work. And so when you're talking about collapsing the wave function, we've defined a probability wave function of a particular particle in a state, and how it moves through time. And it's very easy for physicists and mathematicians to look at things in the complex plane, or to add extra dimensions to make the maths work. You just integrate an equation up, and you can look at it in another dimension. But whether that makes sense to reality, that part, I guess, is up for debate. Like how the actual process takes place at a fundamental level, whereas sometimes we can. Yeah, it's hard to explain, isn't it?
It is hard to explain, and I think this is where there are various theories about how does the process happen. And so when I was a much younger guy, one of the things when I came across this problem, and I didn't realize that somebody else more famous than I actually thought about it this way as well, that the what is essentially happening is that there's some irreversible process that's altering and selecting the states, basically by some type of projection operator that's acting upon it, where it's selecting the value. And so whenever there's an interaction, the value is selected because there's, the probability of the overlap works out. And that kind of gives you rise to this thing called von Neumann entropy, and which I'm kind of going to go ahead and say this entanglement idea and this composite idea is really the rise of what thermodynamic entropy will eventually become, because it's at the most fundamental level. And so anyway, so what Einstein at this point says is that, there has to be some hidden variables that's causing this particle to take on this momentum and this particle to take on this momentum. And we know that it is already determined at the beginning, before they're ever started. And so that is the concept of realism, which was basically the value of the unmeasured quantities are already set before the measurement. This is just, it's called counterfactual definiteness, if anyone's wondering. Probably nobody's wondering, but and
go ahead.
You have locality, which, as we were saying before, and I think that this picture, I kind of like to go into this the resolution of this, but basically that no signal is traveling faster than the speed of light. So, but Einstein was convinced that we had realism and locality, and he ends up being wrong. And I like this argument. I like this kind of setup to discuss what entanglement is. Entanglement's kind of like superposition's like addition of states. Entanglement's like multiplication of states, but you could have multiplication of sums of states.
So maybe one, because we can go into the superposition of states and things like that, and you could go quite deep down that rabbit hole, Hilbert spaces and that, because the Schrodinger equation sort of defines these states, and you can have and you can have a superposition of states. And the discussion, I guess, about fermions, like versus bosons, having
Yeah.
half spin versus whole spin integrals, all that sort of stuff. But maybe what we should do is just a very basic description of entanglement is kind of like if you have a particle in a well, it's a superposition of states, right? But it's basically a probability of being in two states. So one good way of thinking of it is like if you have like a coin toss that could be heads or tails. And I know this is sort of simplifying it, but if for the audience, I guess, to just get a real good understanding of what it is, it's that you can prepare photons or electrons that are entangled, a pair of them, and that they share the same state, the same quantum state. And that state is a probability of being basically in one of two states. Now, if you take these two particles at any distance, and that's the big thing, at any distance, and you measure the state of one of the particles, you instantly determine the state of the other particle.
Yes.
And so the problem with that is that non-locality thing that you're talking about, and this is just really to emphasize the point, is that you can have these two particles at either ends of the laboratory or hundreds of kilometers away, which they have done through measurement, or on the other sides of the galaxy. And the state, the wave function collapse when you measure the spin state of one of these particles instantaneously determines the state of the particle at the other end. So it is, you could,
Perfect.
if you thought that there was some sort of communication between these particles, you would have to say that it's faster than the speed of light, which is of course not what's happening, but that's what it looks like. So that's why Einstein called it spooky action at a distance.
Spooky action at a distance. Here's another example. This is a classical example, so there's some breakdown because you could say, well, there was a hidden variable here. But let's imagine that we take two gloves. One's a right-handed glove, one's a left-handed glove, and then we put them in boxes. And we shuffle the box. We have some thing that's randomly shuffling the box, and we send them across town. And we have one observer, say in on the East Coast of America, and then someone in Australia. They open the box up, and then one sees a left-handed glove. Well, they know that the other recipient has a right-handed glove, and so those answers are now definitive. And the reason I've added the randomness in there was that I didn't want to presuppose which one I was picking. Now, nature is a little bit more confusing than that because nature actually it occupies both states until that measurement is performed, which is what the oddity is. And
yeah, that's actually really interesting. So one of the examples of that is Schrodinger's cat, right? So the idea that you have this randomized whatever poison in a box with a cat, and that you take away all the other variables. The cat is in both dead and alive states simultaneously, because you don't know whether this is a thought experiment, right? So no one's actually done this on a cat, so people can chill. But the idea is that the cat exists in both states until you open the box and you know which state the cat is in. Like that's Schrodinger's cat, right? But the problem with that is that the cat is dead or alive whether you open the box or not, if you know what I mean. So it's slightly different to the actual way that entanglement works, because when you measure the spin state of one particle, you directly affect the spin of the other. So it's not like it had a characteristic or a parameter that we're just uncovering. It actually has no parameter until we make that measurement. Then that determines the parameter of the other. So it is slightly different.
That's why I was saying I really don't like this analogy, but I was trying to put it in more classical terms so people could kind of get a feeling about it. But you're exactly right. It really occupies both states until that measurement happens, But the thing is that, and this goes back to the Einstein, the EPR paper, is that the reason that the two states were entangled, that we can make the precise measurements, that we can know something more than what we should be able to know, and that this argument was sharpened up by David Bohm using well, it doesn't really matter, but he sharpens this argument up quite a bit, and then develops something called two-state pilot wave theory. And so it's a different formulation of quantum mechanics is deterministic, somewhat deterministic. You just need a signal that goes backwards in time. So anyway, so it's in the preparation of the state. So the states came from a single origin, which entangled them. There's information that gets entangled, and the state itself is the thing that doesn't change. You know, it's the state itself is the wave function, and the wave function is not a function of x. It's not a function of position. It's not a function of anything. It is an abstract vector, and so it just exists in this abstract space. Now, you can write it down in terms of a function of position, time, whatnot. But
it's a probability wave function.
That's a probability wave function. So anyway, so I think, Einstein, but this concept of realism and locality is crucial. And this is kind of analogous to how this ends up getting resolved by Bell in 71 or something like that. Was a very common, very similar thing that happens with special relativity in 05 or 1900 to 1905, or he's thinking about these things, working in the patent office.
That's really interesting. Just to interrupt briefly. That's really interesting that we have these ideas where Einstein was building on the ideas of Maxwell and all these guys, and then Schwarzschild comes along and thinks, oh look, hang on, you've got these singularities in your equations for relativity. Then Schrodinger's come, and then they all kind of come together, and then so everyone's building on top of other people's theories, and they're making it sharper, like you say, better. And then after, like say, the 30s, I mean, to be fair, World War II and a lot of things happened, but it wasn't really until the 70s when Bell sort of came up with the theory of how to test it, and then it wasn't even until it was actually measured. But my point was that sometimes these ideas, that they take a long time for people to actually build upon them. They can exist for ages and get put in a dusty shelf somewhere until someone comes along and goes, you know what's really interesting about this idea? And then make an application of it, and then someone builds on top of that, and that's how we get progress and technological upgrades. So I would really encourage people to sort of consider some of these ideas not as antiquated, notions of the past, but rather, fuel for a potential idea of your own that can, flourish and things like that. So that's a really exciting thing about science for me.
Absolutely. It is a building process. It's a building process, and I think there's some historical reasons why that happens right after there's this break. It's kind of this getting kind of off topic, but the quantum electrodynamics, people were making measurements. Dirac's theory is breaking down, where he has these infinities that arise in his equations. He's not sure how to deal with it. There's a few ideas. There's a few ideas. The war happens. Feynman, Schwinger, and company kind of take some early ideas of Hans Bethe and develop the initial phase of renormalization uh, of the quantum field to take care of the infinities. So it becomes more like a computational, like shut up and computate. And then in the 70s, people are starting to kind of go back to the foundational ideas. And, those people get ostracized out of the physics departments. Uh, I'm not really sure what happened to. I know that Bell ends up sick at some point, but you're right. I mean, it's like you don't know where the good ideas are going to come from. But what I was, and I think we've lost everybody, but that's okay. I don't really care. I like this. This is cool. So I think what I was about to say though was Einstein was basically wrestling with the question of uh, what happens at what happens to a light being. What do you observe with a light being when you, as an observer, are getting close to the speed of light? And so you have Newton's equations, Galilean invariance, right? And so the universe is homogeneous isotropic, which basically defines like the structure of the space time. And then you have, and then he says, okay, that's true, but when you apply those Galilean transformations to that electromagnetic wave, it doesn't look like an electromagnetic wave. In fact, it doesn't satisfy Maxwell's equations. And so either the Galilean transformations are right, Newton's laws are essentially right, or electricity and magnetism, and then is right. You can't have both without modifications. And so I kind of feel like the next resolution into what Bell did, it kind of falls in the same logical structures. Like you have realism or you have locality. You can't have both. You can't have something that's locally real.
And I like the idea that you're talking about of resolution, because when we talk about physics principles, we're talking about an approximation to reality, just like a Riemann approximation to a derivative, like through a series of tangents, and it's like you can get close to understanding what is going on, but what you ideally want is to be able to predict its behavior repeatably. And that really is the main goal, is to have experimental evidence that's repeatable at labs across the planet. So this idea of refining ideas, and so Newtonian gravity, works well when you're talking about apples falling from trees. If you're trying to describe orbits of planets around the sun, you need relativistic gravity. And because we actually have satellites in orbit, you use GPS every day, it's these relativistic corrections that actually give you accurate data from your GPS. So it's that refinement of theories and kind of rejecting of a classical theory, and then kind of coming up with something that's more accurate, that works in more cases, that I think is kind of part of or inherent in the scientific principle, in the scientific method.
Right. And I think, in our experience, and this is kind of like the heart of the resolution with Bell, was that our classical intuition, our classical idea of conditional probabilities, it was not what's happening in quantum mechanics. And I think that it's been a while since I've looked at Bell, but I actually came across this example of light polarization and having a series of polarizing lenses. And what happens as you go through successive lenses. Let's suppose that we have a polarizer, right? Photons have two internal electrical. The electric field has two internal degrees of freedom, which come
You
out in
can
the
have
forms.
horizontally, vertically, circularly polarized light. Yeah.
Right. So left-handed, right-handed. It depends on the orientation of the electric field. Right. But there's two degrees of freedom because of Gauss law. Whatever. It
Yeah. So
constrains it.
the electric field of a propagating wave is perpendicular to the magnetic field, and then it's about how, you know, that 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 vector propagates through space, I guess.
Right. And so when you go through a polarizing lens, it selects out 50% of the light, basically, right? And then depending if you have two polarizing lenses, if they are 90 degrees perpendicular to each other, so the polarizing, the selector is 90 degrees, right? You would see zero light coming out of it, correct? So
Yeah, I gave a thumbs up. Sorry.
that's all right. And so, but let's imagine now that we put in a third, a one in between the two. And so, if we have it at 45 degrees, so we have lens A, B, C, and the second polarizer is 45 degrees from the first one.
Yeah.
It's oriented. Then 50%
Sure.
of the light's coming through, right?
Yeah.
To the second one. Well, what's interesting is that there are scenarios. Let's say let's change this orientation up. We have the first one is vertical. The second one is 22 and a half degrees from vertical, and then the next one is 45 degrees from vertical. So what would you expect to happen? Because the polarizing lens is a quantum measurement that it's selecting quantum states to go in from one polarizer to the next. Well, what happens is that it looks like the second polarizing lens is creating light. There's more light that gets passed through to the next polarizer, to the third polarizer. In fact, it goes that 85% of the light from the second polarizer is like from the first to the second, about 15 is reduced, and then another 15 is reduced, and it gets to the third polarizer. And so 15% plus 15% doesn't equal 50% that you should have if you don't have the measurement. So something looks pretty bizarre of what's going on with this, and it looks inherently quantum mechanical, and it is quantum mechanical. I mean, it's a quantum measurement. And so this is kind of the one of the devices that I think Bell was thinking about when it's like a toy model of of these conditional probabilities that seemingly define this not equal to these classical conditional probabilities. Is this making sense? I mean, am I?
Yeah, it is. It is.
Okay.
I think what you're just doing is you're illustrating, that some of these experiments are very counterintuitive, and they only make sense when you consider them as probabilistic, probability wave functions. And one of the interesting ones that I think is very famous, because like that's a very esoteric experiment, and I think Bell's, was an absolute genius to sort of be able to insert the idea of correlation. So he would come up with this experiment where you say, if you did this measurement 1,000 times, to know whether you've measured the spin state of one of these particles, you would have a high correlation, and it would prove one way or the other. And so it took someone else, I think, Kaiser or someone, to come along and actually do the measurement. But the idea was that you could actually do this on a large scale with, hundreds and thousands of photons, and then measure the probability of distribution. And so one of the interesting things as well is there's a very famous example of this one, which you of course are aware of, but maybe the audience has just heard of. But it's the double slit experiment, or sometimes the Young's double slit experiment. But so the idea of that is just that if you sent a photon at a single slit, then you would get a Gaussian distribution, against a wall, and then you measured, you had some sort of photodetector, and you measured the distribution of the, as you detected the particle as it comes through that single slit, you would get a normalized Gaussian distribution. You put in a second slit, and straight away you start getting interference patterns on the wall, which is a wave-like property where you have, if people can conceptualize like a wave breaking against, like a water wave or a sound wave against two slits, you then create two smaller waves that then interfere with each other. And that interference pattern has a very characteristic pattern. So by adding a second slit, you inextricably change how you measure the result.
Right, and if you would immediately then take away, then it changes back. So we're not talking anything about entanglement yet. We're just kind of describing superposition for those that are talking, that are listening. But yes, exactly the same idea. But I kind of feel like it's very interesting, right? Because is this really going to come down to a counting argument? Like how many photons, what's the measure of the number of photons coming through the first pass through versus the second measurement piece, and then the third measurement piece. Now then you could say at that point, well, is there a hidden variable that would basically, this doesn't make sense, because if I remove the second one, I've got 50%. I've got 50% of the number of photons coming through this polarizing lens, right, or this gate, or whatever. But if you remove, but if you put in the device, now I have 85% that's coming through. So there's something that's going on. Does the photon know? And that's really the question. Does the photon know that second gate exists, and there's some kind of communications before the measurement's made? And then, so that's the toy model, the superposition, and then you define what the entangled state is, and so the paper, I believe, or the notion is that I mentioned von Neumann entropy. So if the von Neumann entropy of a pure state, which would be can be a superposition state, but the pure state is zero, but an entangled state is greater than that. And so you would then construct the entangled states mathematically. At least, like I said, I'm a theorist, so I'm like, theories, although physics is an experimental science. And then you would basically do the same mathematical trick and say, okay, these systems have some translational invariance. I can project those out to acausal distances and perform the same counting experiment. And then it just becomes a counting experiment, and saying, I know what the classical probability is, but it is not equal to this quantum probability. And then Bell comes to final resolution and says, no, you cannot. It is impossible that you have a real local quantum theory of the universe. It is impossible. Now, other people have since then come in and said, well, if you have, and this isn't even talking about string theory or anything, you can project the number of space-time dimensions up to an absurd amount and get local variables. But that's, you know, that in itself is um, very unsatisfying and kind of unphysical because there's really
That's
nothing motivating it other than the fact that I want local variables. I
the
need
math.
local variables. I need, it's like, well, sure, but
Yeah,
where does
so
the test come in that you would be able
that
to
goes,
validate those
yeah,
theories?
yes, exactly. So that goes back to what I was talking about when I was saying the mathematical tricks that we sometimes use, physicists, where we can add dimensions to make the maths work out. And superstring theory, whether they settled on 11 dimensions or 10 dimensions, and it's all very theoretical and it makes the maths work, but there's never been any experimental proof of superstring theory. So we should probably not go into that too much. But the
Not today.
idea,
Maybe in a future day. I could go in a long time on that topic, but
oh yeah, yeah. I think it's very fascinating. Superstring theory, like yeah, yeah. But rather than to go down that rabbit hole, one of the interesting things I think about that higher dimension aspect is sometimes, and like I don't know how you think of it, but it's very easy on paper to sort of represent things in other dimensions. But when you start thinking of shapes in higher dimensions, like a tesseract, or hypercube, it kind of there are limits to the human understanding and our projections. Whereas, like, if you look at, say, the volume of a sphere, like, 4/3 pi r cubed, and then you look at the surface area of a sphere is like 4 pi r squared. It's like the surface area of a sphere is, well, is the derivative of the volume. And sometimes you can represent shapes in higher dimensions at using a smaller dimension. And so one of the interesting things to think about, but possibly for the audience, is to try and conceptualize like a 4-dimensional shape where you're looking at it in only a 3D plane, or a 3-dimensional shape looking at it through a 2-dimensional plane. So you're only going to see some aspect of what's going on. You're seeing an approximation to reality.
shadows.
Yeah, so one example, I guess, is like, say you live in a 2-dimensional world, right? X and Y, and you see a sphere passing through your plane of existence. All you're going to see is a very small line that effectively gets larger and larger, which represents, I guess, the diameter of the sphere as it's passing through your plane. That line will get larger and larger and larger, and then get smaller and smaller and smaller, and that would be the sphere passing through. So you would only be seeing an aspect of what's actually happening in because you're limited to the dimensions of your perception. So the idea is quite powerful. And it can be exploited, unfortunately, where people just willy-nilly throw in dimensions and oh yeah, higher dimensions, this and that. But it can be used, if you're courageous, enough to describe the interaction of quantum entanglement between, say, two entangled photons or two entangled electrons that are separated at large distances, where you measure the spin state of one and you instantaneously determine the spin state of the other, rather than it being a communication faster than light communication between these two particles. It's just that they are inextricably linked in another dimension that then bypasses the need for actual data or information to travel at a speed in our 3 dimensions or 4
Right.
dimensions.
Yeah, and I think that hits it right on the head. It's not. I think when people are like, I was trying to get away from this, the notion that you were saying that most people when they experience like a function, it's a x to it's a mapping from x to y to another, from one space to another. But this is really kind of, we're talking about the most abstract way of thinking about a function, right? It belongs to a Hilbert space, which is kind of hard to describe. It's an inner product space. It's complete. Blah blah blah. What does that mean? Well, it's the math. Lots of math that is necessary to describe these processes. But the other thing is like the wave function in itself is non-local, but the dynamics though are inherently local. So you can't have local action on the wave function, but the wave function itself is not inherently non-local. And what do I mean by that? The dynamics of the system is really governed by that Hamiltonian. And if the Hamiltonian has a particular functional form or a particular operator form, you're guaranteed to have locality. It's kind of like the Lagrangian. If which you get to the Hamiltonian, I'm going way too deep into this, but if the Lagrangian is only a functional of the position in the canonical, or the time derivative of the position, then and that the second derivative is non-zero, then you're guaranteed to have locality. But if you say, well, the Lagrangian is actually a functional of position, velocity, and acceleration, then you get a non-local Hamiltonian, which is it would not look like Newton's laws. It wouldn't look like any dynamics that we have. So the dynamics in itself is local, but the wave function. But these are all rabbit holes that we can go down in the future. But I'm enjoying this. I don't know if you are as much as I
Yeah,
am.
yeah. Look, it is really interesting, and yeah, when you start looking at Hilbert spaces and like manifolds and things like that, and you start looking at higher dimensional, spaces and things like that, it is very interesting. It's very hard for the brain to conceptualize these things. Like I said, with the three-dimensional representation in a two-dimensional world, and to think of a three-dimensional cube in 4 dimensions, like a tesseract, like it's hard for the brain to kind of get their heads around. One of the interesting things is about how we talk about space-time, about having your X, Y, Z, and then this time component. But there are some theories where they use multiple temporal dimensions to describe what's happening here as well, which I think is really fascinating, because it's kind of easy to scale a shape into higher dimensions or lower dimensions. Like if you're talking about points, lines, cubes, tesseracts, you're talking about the number of edges, and you're just adding like another dimension of edges, or like corners of a cube, and then you go, well, instead of having 4 corners, it's got like it's got another dimension of corners, and you kind of like, you can kind of think of that. But when you talk about multiple temporal dimensions, so that you can have, and so we've already asserted that time itself is elastic, it's malleable, so that you can, with special relativity, you go super fast, time slows down. With general relativity, you get super heavy, time slows down. So we already know that time is not one of these, and to do with the speed of light being the ultimate speed, that has huge implications. Where if you think about the Milky Way being whatever it is, 30,000 light years across, so for someone to traverse our galaxy, you're talking tens of thousands of years traveling at the ultimate speed. and there's not that many life forms that you can think of that last for tens of thousands of years. So before you kind of like, you know, you look at some of these things in terms of like just the dry and you know the dry mathematics of it, and you say, well, why would we be talking about this? It's because it has huge implications to how you know perceive the world around you, and we use these constants and you know the relativistic equations all the time, but we don't really consider, you know, some of these more philosophical ideas of like having multiple time dimensions and what that would mean, because the brain just kind of goes, huh?
At
and
some point,
but
it just becomes
mathematically,
mathematics, right?
yeah, but
It's,
mathematically you can make it work, you know. So
yeah.
is that a limit in our understanding, you know, or is there is it just a fabrication of mathematics?
Yeah, I think that's a good topic for another day. But that's like ADS, like ADS 5 CFT correspondence. There are two time-like dimensions in ADS 5. So what you're what you're talking about would be like the bulk for the strings to interact, and then they're interacting, and then they have a boundary, which is what they call conformal boundaries, where they interact. But kind of going back to circling back to the entanglement, there's some spicy little things that that this kind of tickles your brain about. And I was actually talking to one of my best friends. I don't want to get doxxed on this, but one of my best friends does some stuff. Uh, he writes a paper, writes an article, popular science article, and he wrote something about entanglement and faster than light travel a couple months ago. And I was asking him about, has anyone ever considered the correlation functions and did the calculations on like de Sitter space, and which would be an expanding universe. So the idea would be like you have all these quantum states at the beginning of the universe. Is there some way that um, you know, everything is basically entangled in some degree. You know, we have decoherence that we may not be able to measure it, but at what degree of entanglement could be found on anti-de Sitter space? And like I said, there's a lot of math in there, but then there's
Yeah,
other
that's interesting. Yeah.
uh, and a lot of people have done this on the ADS CFT with the ADS CFT correspondence. There's a lot of work done on that, but recently there's been some very interesting work where uh, it's pretty complicated. So they take the space time and they can make, even though that the Sitter space doesn't really have a boundary, you can put patches, and then you can talk about like the entanglement entropy in various patches. It's pretty encouraging that people are talking about that, but also there is a connection with Bell and free will, and so I find this very fascinating. I So John Conway, uh, there's a theorem called the free will theorem, which basically would indicate that if you yourself have free will and you are comprised of quantum particles, because of entanglement, because of all the math, the special math, that the electrons themselves and the quantum particles that you have are made also have some level of free will, which means that the future state doesn't necessarily depend on the past state, which is runs counterintuitive to the notion of you know action on the quantum field. I mean, I think those kind of ideas are very wild and spicy.
Yeah.
That you can
There is
get
some,
into this. This is
yeah,
maybe what we
very,
should have
very
started
wild.
out with instead of the formal stuff, and be like, okay, well now we're going to talk about the formal stuff. But yeah,
Well,
I mean,
I think some of the implications of that, like you say, a bit wild. Like, and and whether you believe in a deterministic universe or not, and all that sort of stuff comes into it. But and
There
there's
are,
also there's a great science fiction aspect to this as well, right? So you can it becomes philosophy at some level, because you can't measure it, unfortunately. But
well,
you could
physics
speculate. Oh,
is
sorry, but
the beginning of physics is philosophy. It really is. It's the philosophy of the natural world and how things
yeah.
work. And so,
Yeah, yeah, and I think that's crucial to the scientific method, is to wonder how and why, and that curiosity, and look, I some of the science fiction stuff that that you see in these old Star Treks and things like that, they just people took those ideas and were like, well, hang on, why can't we do that? Well, why can't we do some sort of hologram, whatever's touchscreen? So humans are great at taking scientific ideas, science fiction ideas, and actually turning them into real science. So I should preface what I'm about to say with, like, that I'm not discounting science fiction. But one of the things that you can do when you look at quantum entanglement is that you could say that there's this multiple realities, many worlds theory, parallel dimension idea, where you measure the spin state of one of the particles, and it immediately determines the state of the other. But in a parallel universe, the other thing happens. Or, for every measurement that you make where there's like a probability aspect to it, there could, when you collapse that wave function, you get a split in reality, and you have these ideas. I don't subscribe to that, but it is interesting to think about.
well, there are measurable consequences. So that's the Everett interpretation or theory of quantum mechanics, and there are measurable consequences. But it's almost like it's again, this is not my field, so I'm just going on some colloquiums that I've seen, seminars that I've went to. I found the work, very entertaining and interesting, and perhaps given enough time, perhaps if let's make this crypto, let's say Hex or Chia or whatever crypto that you may be into goes up, then I could spend some more time thinking about these things. Uh, but you, I
Yeah,
saw
yeah.
Chia guy come in here, so I was like, oh, let's plug Chia. Uh,
Well,
so
I'm going to represent Hex, so I think maybe you could put the highest of stakes documentary trailer in the nest or something, and that
right,
could give some people something to do while they, instead of listening to us gas bag too much. But
right,
um,
pontificate, yeah.
one of the things I was going to say is, yeah, you can, if you're going to add stuff to the nest. There was that article I think I sent you. I might have to double check that I actually sent it to you, but it was very recent, and it was just like a science magazine thing, where they were talking about quantum computing, and it was like they'd done a calculation using, it was Google's big brain computer, the quantum computer that they did, and so it was like within a few seconds they had performed a calculation that had taken previous supercomputers 47 years. That what they would simulate would take the best supercomputer 47 years to solve. So I don't know if you've got that Science Alert article, but it's
Um,
certainly something that. Oh yeah, here we go. So the
so
Frontier supercomputer.
how does quantum computing? That's a great place. Let's start there because this is
Yeah,
very pertinent. So how does quantum computing? This is one question I was asked the other day. Is is your brain a quantum computer? And I instantly said no,
ooh, no.
no. And it's a technical. This seems like it's a technicality because it's like your brain is ruled by quantum mechanical processes, but your brain in itself is not a quantum computer. So
Yeah, so the brain
The,
uses neurons and neural pathways and firing neurons and things like that. And I guess it's analogous to how a computer, switches bits through transistors in silicon. But whereas a quantum computer, it's using the two states, and the qubit, the quantum bit, it kind of represents the probability of being in these two states. So that is very different.
very different, and they are entangled states. It's not only that they are that they,
Yes, yes.
so to do a quantum computer, you have to have an ensemble of a lot of these qubits, and they're performing various calculations with that using the principles of superposition, right? But the entangled piece is hard to do. It's very hard to maintain that entanglement, because it's really, if it interacts with the environment, it becomes decoherent, and you lose the interaction between the electrons, right? Did I lose you?
Yeah, yeah. So the decoherence. So you have a decoherence, unfortunately, when it comes to storing, entangled states, and so yeah. So that's the. So there's different ways of producing these entangled states, through cooling them down to, uh, superconductive sort of levels. And there's all sorts of interesting physics that goes on when you talk about Bose-Einstein condensates at these ultra low temperatures. But I think the way that they typically produce them is just by firing like a laser or something at like a calcium atom, and that produces entangled photons. But there's ways of doing it using fiber optics, um, and but yeah, effectively the problem is not so much creating them, but it's stopping them from interacting and losing their entanglement, um, uh, by interacting with other things around them.
Right. And eventually, this will become an issue well, there's some discussion, right, with cryptography. The quantum computing could, break RSA encryption with elliptical curve encryption and whatnot. But then there are other encryption techniques that are more quantum resistant, and so eventually, I mean, I think I was look. I mean, uh, Vitalik was talking about that the hashing in Bitcoin is quantum resistant up to a certain point, and then but then there are other cryptography methodologies like lattice. There's an active thing, but every time people start talking about AI, AI, quantum computing, and how it's going to upset the crypto market, I'm like, they're so far away. IBM is the cutting edge for quantum computing. They're far away from having a commercially viable quantum computer. And even after that, after the quantum computer, the processing piece is done, then you have all the transistors, and you have a lot of technology that has to be developed before you implement it into a commercially viable system.
Yeah, I guess that there's a big difference between a lab grade supercomputer and a commercial viable system. So, from compliance and stuff that I'm involved in and all that sort of stuff, it gets complicated and very boring. But I guess the capabilities of some of these quantum computers, though, it is accelerating at a tremendous pace. To have this Google AI supercomputer, and I tried to add it to the nest, but I couldn't. Uh, but um, it could do the calculation in a few seconds that frontier supercomputer would take 47 years to crunch those numbers. The implications of that are non-trivial with regard to cryptography, because when you do look at some of these 12-word, 24-word seed phrases and things like that. And then if you look at a brute force method of cracking that encryption, it is a astronomical number, right?
Right.
But when you start looking at it, and it's not AI that I'm concerned about in terms of cracking this, but when they scale the number of qubits up in these quantum supercomputers, they
Right.
do it scales, exponentially how many
Correct.
processes they can do. So, and if you kind of think of, Moore's law about how technology kind of, the doubling rate of technology and things like that, it is a little bit concerning that at one level, at some point in the future, we might have quantum computers that could crack, uh, you know,
I
12-word seed phrases and things like that.
I absolutely believe that that's within the realm of possibility. I just question the amount, the time framing of it, because I mean, when we're talking about the qubit, the entanglement problem, I just wonder, you know, there's a limit to how many qubits that they can actually get entangled, and without,
I think they're up to 70 qubits now.
yeah, 70. So perhaps. I
Yeah.
mean,
So
it's
so
going to
when
be
they were,
it's an engineering
they,
problem. I'm like,
yeah, it's something out of bloody Star Trek. When you look at this quantum computer, the Sycamore one, it's out of control. It's just, it blow your mind when you look at it. And you know, to think of, when they were talking about this quantum computing overtaking regular supercomputers like the Frontier supercomputer, um, that quantum supremacy idea, that the quantum computing is now, you know, superior to the other supercomputers. That that has passed. That's been and gone. Because that was, I think they were only at about 54 qubits or something like that, where that was
hmm
when IBM and Google were arguing whether or not, they had reached that quantum supremacy. But now at 70 qubits, I think that argument is now done. So, it is kind of interesting to see that, you know, and so this all of this quantum computing stuff, like this at a very fundamental level, is because of quantum entanglement.
right, exactly. It's all because of quantum entanglement. No matter how difficult the engineering problem. That's what I mean. What I don't really mean to demean engineering. It's engineering is necessary, but the truth of the matter is, it usually kind of goes from like the physics, the fundamental physics of a situation, of something that's very simple, to something earth shattering like a quantum computer, and how we may have to change our complete, all of the code for encryption would have to be changed. Uh, there's other things that make me worry about the Riemann hypothesis. Also makes me really nervous about encryption in the future. That, but quantum computer definitely could within the next 20 years for sure.
And so, what about the possibilities of, like, with quantum key distribution? You know, you've got this idea that you can have a secure channel where you can use quantum entanglement or quantum teleportation, however you describe it, a transport of information using entanglement, whereby a listener or eavesdropper that is trying to hack that secure channel would actually affect the measurement and would be detected by the intended recipients of the message.
Yeah, that's a pretty fascinating. I haven't really thought about it, about
Yeah,
that
so
particular
well,
aspect.
it, it's very straightforward if you think of it as just being like, the classic Alice and Bob sending a message to each other using an entangled um, uh, series of bits, right? And then once, so they can measure the spin states, and they can have like uh, a key where they've basically measured all the spin states. And then in a public channel, they can exchange information, almost like a zero knowledge proof, where you can
Mm-hmm.
infer from what they've said um, using your key to decode the message. But if someone has intercepted or tried to measure any of those entangled photons along the way, you get that decoherence thing that I was talking about, where you know you've interacted with the particles, you've affected the spin states, it no longer transmits that information to at the other end, because when they can tell that the spin states have been altered, so that they know that someone has is eavesdropping on that channel. Whereas if you've got a true uh, you know quantum entangled communication path, you could prove that it hasn't been intercepted in any way. Otherwise, those spin states would have been changed, so
Would have
that
been
line is
altered.
secure.
Yeah.
Yeah, yeah. So
Wow,
there's interesting.
that is very interesting idea. So this,
Yeah,
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 again, this is kind of amazing. This is what we're kind of alluding to, is like people building their work on each other. This is almost, it's the solution before the problem, right? And I think that's
yeah.
this kind of field
And that,
is important to do that. you know, is this
yeah. I
worthwhile? Is
mean,
this ethical for us to continue down this path of building this, even though we know that we have to change all these protocols? We have solutions for that. You know,
yeah. Look, I think standing on the shoulders of giants is always a good idea. It's always a
absolutely.
good idea, and that's what you know projects us into the future, is by and propels us forward as a species, is that we learn from the mistakes of the past, and we learn from these other things and these experiences, and we take new ideas and kind of build on them and build. So I'm a huge fan of building on ideas. Only later is that magnetic fields propagating through space. You measure these things at different frequencies. It basically determines our entire communication. So like how we transmit FM radio or TV or any of this stuff that we, comms at any level, mobile phones, whatever. It's all electromagnetic. But gravity waves, being a perturbation in space-time, a ripple in the fabric of space-time, is another way to measure, like another spectrum to measure, say, coalescing black holes or whatever. Um, but we've only just touched the surface of this spectrum, of being able to just even to detect, the most massive things in our universe, colliding and going,
Right.
oh shit, we can measure something in this spectrum. But it's not to say that in hundreds of years from now, they might have just refined that technology, so you don't need, interferometers that are, kilometers long, and you can just be like, oh yeah, I can measure gravity waves on my phone. And actually
Yeah.
I can modulate gravity waves and send comms back and forward, just using gravity waves spectrum. And so we
Well,
don't know how this shit
gravity
sort of
waves.
works.
We don't even know if gravity waves, and it's actually, this is kind of interesting that you bring that up. It's like, uh, depending on which, there's theories, obviously, that there are higher actual physical dimensions, and so gravity. One of the notions is that gravity is so weak because it travels throughout all the dimensions, and that you're able to communicate with them, with people using gravitational waves. And that was one of the plot threads that Kip Thorne was trying to bring across to Nolan, even though he kind of took it a different way in Interstellar. When they're when you see the dust particles moving, that was
Interstellar.
all
I'm trying to learn that on piano at the moment.
it was all gravitational waves interactions, but in the original script, and they're like, oh no, it's feelings. I'm like, yeah, that and free will.
It's the power of love.
But anyway, I think it's the power of love, right? Exactly. Well, anyway, I've
Love
really
squared.
enjoyed. Yes, I've really enjoyed this. I think we may kind of work on the formatting a little bit, maybe to have it
Look,
less free forming.
I would love to have people ask questions.
Absolutely.
If anyone wanted to, join this space or future spaces, and ask questions, because sometimes we can get sort of, excited and go down a rabbit hole, but then we don't know whether or not someone has understood that very first concept, and you don't know, the audience at what level that they're understanding. So it'd be good to get some feedback to just kind of go, oh no, we mean this, or I like this idea, but no, I think that's pseudoscience or whatever.
Exactly. It's not precisely defined. And that's the other thing is like most people when they talk about science, and it is very specific what we're saying. It's not, we have observations, we have experiments, and we have hypotheses that we're testing. We're constantly testing. We're never trying to prove something's correct. We're saying, is this falsifiable? Is the theory falsifiable? Is it making specific, and specific claims? And I'm like, quantum theory is the most precise theory that man has. I think if aliens descended, I had a professor one time, and he's dead on right. He said, if aliens descended onto the earth and they were to say, bring us the most beautiful thing that you have, he would bring them quantum electrodynamics. He would first start off with quantum electrodynamics as the quantum field theory of the interaction between electrons, positrons, and the electromagnetic field. So he's like, this is the most beautiful thing we have. We can measure this quantity to 12 decimal places, and our theories predict it within 12 decimal places, and this is beautiful. And like, so it makes very precise statements, not vague statements. And then when people make vague statements, they mostly it's to trick them, and science is to try to eliminate the tricks. But anyway.
And physics is specifically an exact science, so it's not subject to interpretation. We're measuring known quantities that have a value and they're repeatable, and experimental scientific method is repeatable around the planet. And I think that's what gives it the credence, because it's not a theoretical kind of philosophical idea. It's something that can be created and recreated in a laboratory.
Anyway, it's midnight here, so I'm
that's cool. No worries. Well, just before you go, just one thing, because I forgot to talk about it earlier, and it's a bit of the sort of science fiction sort of aspect of it. But so with these quantum entangled states, we can speculate as to how this information is sort of there's two aspects to it. One, you could speculate as to how the information is communicated between the particles. And one idea is that you've obviously heard of the Einstein-Rosen bridge theory, like the wormhole sort of theory, where it's actually there's a wormhole between these two particles that are transmitting the information. And so there's also, you know, this idea that they are actually the same particle, and they might exist in two spaces at the same time, if you know what I mean, because rather than being two separate particles that are entangled and you're measuring the spin state of one determining the other, they're actually the same wave function, the same particle, and that they actually exist in two points in space, but at the same time. So, but that's slightly different because you get the opposite spin states. So, but I do like that idea of the Einstein-Rosen bridge between them, to kind of as like a science fiction-y kind of way that people kind of explain how these particles are communicating in this through this other thing, and it does draw implications to when you have black holes at the center of galaxies, right? Like we have Sagittarius A at the center of the Milky Way, an active galactic nuclei at the center of most galaxies. So when you have these black holes and you have this breakdown of physics and the singularities, you know, this idea that there could be these Einstein-Rosen bridges between black holes is a really interesting thing. And that maybe what we're seeing when entanglement is just a very sort of a basic level, an Einstein, like a wormhole between these two particles that exchange information. So that's a little interesting science fiction-y kind of idea that I thought something just to throw out there for people to think about. Yeah.
Well, and then I mean, there's so much to go on, but I think actually that may be a good place to kind of springboard into future discussion on quantum gravity, because what you're kind of describing is that, you know, I said at the beginning of this episode that general relativity, which is a description of gravity on a galactic or large scale solar system, galaxies, formation of black holes, is inherently a local theory. But then you have quantum mechanics, who is inherently now non-local. This is at the edge. This is at the edge of resolution. Now you may say, well, you have quantum field theories, yes, but this is at the edge of the conflict. And so I think that's probably a good place to stop tonight. Maybe we'll awesome. Figure out. Yeah, I've really enjoyed this. I know that probably put most of the hexagons asleep, even the chief folks,
Look,
they vanished. But
if nothing else, if nothing else, we can act as a good sleep remedy. You know, listening to Graviton's dulcet tones, you know, to help you drift off to sleep as we discuss quantum mechanics. If nothing else, that's a service we can provide to the community. But look, I like talking about ideas and concepts, and I like, you know, building on these things. And I think that people shouldn't shy away from this stuff. I think it's there's more interesting things out there in science and reality than sometimes that we can make up. So you just have to go down that rabbit hole.
Absolutely. Well, I'm going to call it a night, and we'll work together and try to come out with a better maybe format where we're kind of. I like your question and answer idea. Well, I appreciate you, and I appreciate you.
No worries.
Yep.
Thanks very much.
Thanks for stopping by.
Yeah. Thanks to the listeners, and thanks to you, Graviton, for the idea and for having me. And hopefully we can do it again soon.
Absolutely.
Cheers. All right, mate. Have a good one. I hope you get some rest.
Okay, you too.